All right, welcome to The Explainer. Today, we're basically going to become mathematical detectives. We're setting out to crack the code hidden inside polynomial graphs. And trust me, by the end of this, you'll be able to look at an equation and see its secret shape. So, every mystery has a starting point, right? And ours begins with an equation, a polynomial that looks something like this. Now, it might just seem like a jumble of letters and numbers, but it's actually hiding a picture. And that's the real question, isn't it? Can you look at that and see the hills and valleys that are locked inside? Because the shape of a graph, it holds secrets, and our whole mission today is to uncover them without having to plot out every single point. Okay, let's dive right in. Every great detective needs that one key clue, that master key that unlocks the whole mystery. And for us, believe it or not, it's hidden right there in what's called the degree of the function. This one simple rule is going to be our master key. But first things first, we need to know what we're actually looking for. We're on the hunt for turning points. Now, these are just the spots on a graph where the line changes its mind. It stops going up and starts heading down, which makes a hill. Or it stops going down and starts heading back up, creating a valley. So let's circle back to our prime suspect, that equation from the start. Our very first clue is the highest exponent we can find. In this case, that number is a 4. This little number is the single most important piece of evidence we have. It's going to unlock everything. And this brings us to the big reveal, the secret weapon in our toolkit. It's a simple but trustly, incredibly powerful rule. You just take the degree, which we call n, and you subtract 1. That number tells you the absolute maximum number of turns, the most hills and valleys that the graph could possibly have. And this is where it gets super useful, because this table gives us a kind of visual forecast. If you have a degree 2 polynomial, it has at most 1 turn. That's our old friend, the parabola, that classic U-shape. A degree 3 can have up to 2 turns, which often creates a kind of S-curve. And a degree 4, like our example, well, it can have up to 3 turns, often looking like a W or an M. As you can see, the higher the degree, the more complex the roller coaster can get. All right, so we've got the basics down. We know how to find the speed limit, the maximum number of turns, but not all turning points are created equal. The next phase of our investigation is figuring out the difference between the local hills and the giant chart-topping mountains. And this chart just lays it out perfectly. Think of it like this. A local maximum, that's the tallest building in its neighborhood. An absolute maximum, that's Mount Everest. It's the highest point on the entire map, period. So a graph can have a bunch of local hills and valleys, but it can only have one absolute highest peak. Okay, we've got our detective tools. We've got the n-1 rule. We know the difference between local and absolute. So let's put them to the test and crack a few case files. So check this out. It's the same simple process every time. Take that first function, highest exponent is 5, so at most 4 turns. Easy. The second one has a degree of 4, which means it can have at most 3 turns. And for that last one, with a big degree of 7, it could have a maximum of 6 turning points. It's a really quick and powerful first glance. Okay, but what happens when you don't have the full story? What if you don't have the equation, just a bunch of data points, like evidence collected from the scene? Well, we can still find the turning points. All we have to do is follow the numbers and watch the trend. Look here, near x equals -2, the y values go from 10, they drop all the way down to -2, and then they start climbing back up to 3. That's a valley, a local minimum. Now look near x equals 0. The numbers climb from 3 up to a peak of 8, then start falling again to 5. That's a hill, a local maximum. And we see one more turn near x equals 2, dropping to -1 before shooting back up. So that's 3 turns, case solved just by looking at the data. All right, let's flip this on its head for a second. Let's try working backwards. Say you see a graph out in the wild, and you count 5 turning points. What can that tell you about the equation that made it? What's the minimum possible degree? Now, your first thought is probably just to add 1, right? 5 turns, so the degree must be at least 6. And you're on the right track. But there's a little twist here. A polynomial doesn't always have to use its maximum number of turns. It can have the max, or the max -2, or the max -4, always dropping by an even number. So a degree 6 polynomial could have 5 turns, or it could have 3, or it could have 1. Since 5 is on that list of possibilities, the minimum degree is indeed 6. Okay, every seasoned detective knows you have to watch out for the red herrings, the false leads that can send you completely off the trail. So let's talk about the big ones in this line of work. This right here, this is probably the #1 mistake people make. They hear that n-1 rule and they think it's an exact number. It's not. Remember, the rule gives you a speed limit, not the exact speed your function is going. And if you need proof, look no further than this. Take this simple function, x to the 5th power. It's a degree 5 polynomial, so according to the rule, it could have up to 4 turns. But look at it. It has 0. It just keeps on climbing forever. Some functions just don't use all their possible turns, and that's totally okay. So, let's lock in these 2 key takeaways to avoid those traps. First, always, always, always remember the magic words "at most." It's a maximum, not a promise. And second, keep in mind that odd degree graphs, the ones that shoot off to both positive and negative infinity, they'll have local hills and valleys for sure, but they can't have an absolute highest or lowest point. So, you might be thinking, okay, this is a cool math puzzle, but why does it actually matter? Well, it matters because these shapes, these graphs, they aren't just lines in your textbook. They're models for how the real world works. I mean, take economics. These curves can literally model a company's profit. And those turning points? Those aren't just bumps on a line. They are the most critical points of the story. They represent the peak profit, the sweet spot, or the break-even points where things start to change. Knowing how many turns are possible helps people predict how many times a market might shift. And that really is the big question this all leads to, isn't it? It's one thing to know about how many peaks a profit curve might have, but what if you're the CEO and you need to find the exact peak, the exact price that will maximize your profit? Well, finding that precise location, that's your next adventure, and the map you'll need for it is a powerful tool called calculus.